In the name of God, hi to all students, and I hope to be fine and have good time. As we discussed in the previous sessions, we reviewed and studied some dimensional reduction, SVD, PCA, and ICA. And we discussed about the characteristics and features of those algorithms. And now in this session, we want to review and study dynamic mode decomposition, and in a shortened phrases we called it a DMD. The reference for this PowerPoint is a book that I will send it to you and I will upload it in the LMS, and also you can also see this topic in again reference C, part 3, chapter 20. Chapter 20 is dynamic mode decomposition. Okay, both of them are good, but this reference DMD book has more details about DMD, and also if you are like to study more in the different chapters, you can see the application of this algorithm. Okay. In SVD, PCA, and ICA, if you remember, you decompose a static matrix to eigenvalues and eigenvectors. For example, in SVD, you can directly by mathematical equations can calculate eigenvalue and eigenvectors. In PCA, you calculate the covariance of matrix, and then after that you extract the eigenvalue and eigenvectors of the covariance matrix, and in this way you can access the principal direction of the data, and we said that these principal directions are related to the directions that the variance of data are much more comparing with other directions. And in ICA also you can access the source, different sources that affect on the data. In those algorithms, we don't and we didn't attention to temporal changes during data. But sometimes we have a dynamic data. For example, the data related to fluids. Then in this data, a better candidate for decomposition and for processing and analysis is DMD, because as you see here, DMD a powerful new technique for discovery of dynamical system from a high dimensional data. This dynamical system and high dimensional data is more important for using DMD. And by using DMD, we can access the spatial dimensionality reduction techniques. Besides, you also can consider the temporal changes by using Fourier transform in time. For example, consider here this fluid in the left. the fluid long time changes, and in each time you have a figure, you can take a photo of that fluid, of course by special instrument. Okay, then you can gather different snapshots a long time for fluid changes long time, and then after that you convert each snapshot to a column of a matrix like X. Okay, for example, x1 here is a vector of this snapshot. x2 is related to this snapshot of x2. Then if you have m snapshots, then you can have m vectors, and then we replace these vectors in matrix like X, but the number of columns of matrix X is m minus 1. Okay, and the column of X prime is the number of columns of X prime is again m minus 1. Why we reconstruct the matrix X and X prime? Because we need it for a DMD. Okay, then the size of matrix X is n by m minus 1, and n, the number of rows, is related to the pixel, to the number of pixel in a snapshot x1, x2, x3, and others. Okay, then after that you can select according to the decomposition of something. You can select the number of principal eigenvalues, and finally you can access the principal snapshot. For example, in this data, 3 snapshots are more important. Then, according to DMD algorithm, you can predict the next snapshot. For example, in a new snapshot K plus 1, using A matrix, you can predict the figure and the fluid in the snapshot of K plus 1. Okay, and A here is the multiplication of X prime and X pseudo inverse. Then in totally, generally we can set that DMD applications of diagnostic. Here you can see, and also you can state estimation and future state prediction. And if you can estimate, you can control the system, and you can do some processing on the system, for example, to do something or not to do something. Okay. As I said in the previous slide, then after we preparing X and X prime, that I said how we make this matrix, we can say that there is a relationship between X prime and X, and this dynamical system in the form of matrix, we can say that there is a matrix A that relate X and X prime. X prime is related to snapshots greater than the snapshots of X. Attention that in X the vector, the columns is related to snapshot of x1 to xm minus n. But in X prime, the vectors, the columns, are related to x2 to xn. And another thing that n is related to the number of pixels and m is related to the number of snapshots. And it is clearly and obviously that n is more greater than m. In the previous sessions, we said that we can decompose x is our data, our measured data. We can decompose it using SVD, and we can access the eigen vectors and eigenvalues. Okay. And according to this equation, x prime is equal to a multiplied x, we can calculate a from here, because in this equation we have x prime, and we don't know a. Our question in DMD at the first time is to calculate a. What is the relationship between x prime and x? Okay. Then, according to matrix function, we can say that okay, x is nearly equal to x prime multiplied by x pseudo inverse, and according to the SVD decomposition, we can replace this decomposition in this equation. X prime multiplied with sigma minus u star. We explained it before. Okay. Here then consider this, and here is mathematical equations that again said that how we can calculate a. Here we see that x prime is equal to a multiplied x. Then we multiply this equation by u star from left. We multiply u star, and then we replace the SVD decomposition of x in this equation, u sigma v star, and then after multiplication we have this, and then from the right we multiplied this equation by v sigma minus, and then by this multiplication sigma v star multiplied v sigma minus is I. Then we don't have this matrix in the left, and then if you remember the SVD algorithm, at the end of the slide we said that okay, we can decompose a and we can access u as eigenvectors from this equation, u star au. Then we can replace the estimation of a like this. Okay, and on the other hand, we can access the eigenvectors and eigenvalues of a tilde from this equation. W is eigenvectors, and lambda here is eigenvalues of a tilde. Okay, and in DMD said that the eigen mode, here we call the eigen mode phi is equal to X, Y, sigma minus W. W is related to the eigenvectors of A tilde. Y and sigma minus is related to the decomposition of SVD of X prime. Okay, and they said that okay, the eigenmodes is equal to this. But if you attention, phi again is a statistic. We don't see any dynamical parameter here. Then for temporal dynamic curve, we can consider t is equal to exponential omega t multiplied b. Okay, b is a parameter. Then we can select it. And the more important thing is here is omega. Omega is a logarithm lambda divided by delta t, and delta t is related to the temporal differences between snapshots. Then finally, and b here, as I said, is a parameter, is related to initial values that's related to this. At the, for example, at the time 0, at time 1, we can calculate b. And then finally we said that okay, the x hat, the estimated, we can reconstruct the data again. As you see, we can reconstruct data by using the principal component of PCA. We can reconstruct the data by using the eigenvectors and eigenvalues of SVD, and also you can show that we can reconstruct the data using ICA methods. Here again, we can also reconstruct data by eigenmodes and temporal parameters. In summary, DMD decomposes the data into coupled spatio-temporal patterns, spatial modes phi, and their corresponding temporal dynamics. And here is an example. We consider F1 and F2. We mix it. Here in C, you can see the mix of F1 and F2, and we decompose X by using DMD, and again we reconstruct the X by using DMD. In the figure, we can see the reconstructed data, and you see that they are so similar to each other. Again here, for a previous example, you can see after mixing data by using the DMD, we can access the singular value. This diagram shows the singular value changes. You see that there are very differences between the first two singular values and others. Then these two singular values are more important. Then we select only these two singular values. Okay, and we can access the temporal function and spatial function using PCA, ICA, and DMD. And in these figures, for example, if the true figures are in blue, and the red is in the DMD, you can see that the blue and red are so similar to each other in both of the temporal and spatial. And also here you also see that the errors between the true one and the mode of DMD, PCN, and ICA, and see that the errors of DMD is 2 less than other modes. In the DMD book, in chapter 1, you can see the code, the MATLAB code of DMD, and also the MATLAB codes for this example. Please run it in your MATLAB and see the changes and the result of DMD, PCN, and ICA modes. Okay, thanks for your attention, and please study these chapters, and if you have any questions, ask me in Telegram group or in an online sessions. Have a good time.